Our next exercise involves the use of a rotometer instead of a bubble burette to calibrate the flow rate going through a pump, the amount of air that's moving through a pump every minute. A rotometer is just simply a plastic device with a column in it and a small ball that as the air is being pulled through it, the ball, faster the air is moving, the higher the ball goes. And this is graduated so you can read how many liters per minute of air that ball indicates is moving through this tube. It's very durable, it's hard to break, it's easy to carry around, it's lightweight, can easily be stuffed into a pouch with a pump and so on and so forth. So it's really, in the field, it's very often used as the measuring device to determine the flow rate for the pump. It's not as accurate as that bubble burette. So that's a problem. The single largest error that we frequently encounter in doing air measurements is calculating the volume of air that we've sampled, especially drawn through a pump. So we need that rotometer to be as accurate as possible. So instead of just using it the way it comes out of the box, we need to calibrate that rotometer using a more accurate standard. For our purposes here, we're going to call that a primary standard. We're going to calibrate this rotometer against that primary standard so we know how accurate this rotometer is, and we can adjust the rotometer for any small errors that may be inherent in it. So in order to figure out how good this rotometer is at measuring volumes, we're going to set up a sample train, as we did before. Except this time, again, we don't have the trap. We didn't have the trap available. So instead of going just from the burette to the pump, we're going to go from the burette, draw air through the burette, through the rotometer, and through the pump. So air is moving through here at the same rate through all of these devices. Okay, now what we're going to do is we're going to set the pump on a low setting. And while it's on a low setting, we're going to let it stabilize for a few minutes, and then we're going to take a reading on the rotometer. Say, for instance, the rotometer says that air is flowing at 1 liter per minute. Well, we really don't know how accurate this rotometer is at this stage, so we're going to record that 1 liter per minute, but then we're going to start a bubble flowing through the bubble burette. And we're going to time how long it takes for 1 liter of air to pass through the bubble burette in order to determine what the flow rate really is, this being our primary standard and this being our secondary standard. So if it's really 1 liter per minute, we would expect it takes 1 minute or 60 seconds for air to pass through this bubble burette, for that bubble to pass through the 0 point and the 1 liter point. Okay, so that would be if this rotometer was perfectly calibrated, perfectly accurate. Well, in fact, we're going to give this a try. We're actually going to try it several times. We're going to try it when we have a low flow through the pump, say about a liter per minute or so, right? And we're going to get a reading. We're going to take how many seconds it takes, what the rotometer reading is in liters per minute. We're going to also record how many seconds it takes for the bubble to take its course through the bubble burette. So we got two readings, liters per minute from the rotometer and seconds from the burette. Then we're going to speed the pump up to a slightly higher speed. We're going to take a reading on the rotometer again and how many seconds it takes for the bubble to course through the burette. A third reading and perhaps even a fourth reading. More readings, the better, right? So we're going to have this pump is going to be sampled. We're going to take readings from the rotometer and the burette when the pump is running low, medium, high, and higher, right? So 4 for our purposes. Okay, so let's take a look at what those might look like. So here's our recording of sample results that we might have gotten from our rotometer. Okay, and let's say that we started the pump, our first test, we started the pump. The rotometer says it was flowing at 1.1 liters per minute. And we found that it took 63 seconds for the burette, for the air to pass through the burette. Then second time we sped up the pump, and the rotometer said it was flowing at 2.3 minutes. Okay, and in this case, as it turns out, it took 30 seconds for the bubble to pass through the burette, and the third time, 3.2 liters per minute, 4.5 liters per minute. So we have four sets of data pairs for the rotometer and for the number of seconds it took to go through the burette. So we're going to convert the number of seconds into the liters per minute, same as the flow rate for the rotometer, that number of seconds represented. I'm going to calculate by saying it's equal to 60 divided by the number of seconds it took for it to go through the burette. And I'm going to hit enter, and it turns out that it's actually moving a bit slower than 1 liter per minute through the burette. We could tell that because it took more than 60 seconds for it to course through the burette. So 1 liter would have been per minute would have been 60 seconds. It took longer than that for us to get a liter through. So it's really at 0.95 liters per minute. So the rotameter is reading a bit high. So I'm going to repeat this calculation for the next 4 readings that we took. And we can see that when the rotameter was reading 2.3, the more accurate reading would have been 2. 3.2, the more accurate reading would have been 2.8, and 4.5 should have been 4. Now, these are extreme. I kind of made these numbers up, so I probably wouldn't expect the difference between the burette and the rotameter to be quite this difference, but I want to illustrate now what we can do with this information now that we know it. I'm going to take this data, I'm going to move it over here. I'm going to take the rotameter flow rate, I'm going to copy it. Let's hit copy. I'm going to paste it here. Let's say paste special, and I'm going to tell it I only want to paste the values themselves. Okay, so there are the values for the rotameter. Okay, now next to that, I'm going to paste the values for the burette. And I'm going to paste it here. I'm only going to paste, I'm going to say edit, paste special, and I'm going to tell it I only want to paste the actual values, the numbers themselves, not the formulas. Okay, so now I can see that this is the rotameter values. Okay, that's really all I need there. And this is the burette values. Okay, and I'm going to truncate that a little bit because I don't really need all the rest of that. And up here, I'm going to put that this is going to be our calibration rotameter calibration chart. Okay, now Excel will allow me to graph these values. I'm going to highlight this. This is going to appear on our x-axis. This is going to appear on our y-axis. Going to highlight this, and then I am going to go up to, I'm going to insert a chart. The kind of chart I'm going to insert is going to be a XY scatter plot. Well, what's an XY scatter plot? XY scatter plot is each one of these dots represents this data graphically. So in other words, let me move this over a bit. So in other words, we look at this data. This first point, the rotameter read 1.1, but the more accurate value was really 0.95. And here, the rotameter read 2.3, it looks like. But the more accurate reading was the burette, which was 2, and so on and so forth. So we can actually draw a line connecting these, and you can do that in Excel as well. Or you can actually graph this manually if you wanted to onto a graph paper if you would prefer. Insert chart. I want an XY scatter plot, and I'm going to ask it to add a curve for me to this add curves connecting these points for me. And there's our connecting curves. Okay, so at this stage now, let's say I take my pump out into the field and I connect my rotameter to my pump. And I start my pump up, let it run for a couple of minutes, and I notice that the rotameter is reading exactly 3.0 liters per minute. Well, I know this rotameter is not perfectly accurate, so I can correct that reading on the rotameter by using my calibration chart. So I know that if the rotameter says it's exactly 3.0 liters per minute, the actual rate at which air is going through the pump is really 2.7 liters per minute, okay, which is what we would have gotten when we applied if we had connected the burette instead of the rotometer. So I was able to correct my rotometer to get a better flow rate measurement than if I just used the rotometer as it came and just assumed that it was accurate. Okay, so as part of your second exercise, if you don't have these numbers and these numbers for 4 sets, I'll give you a set of data that you can use. If you have it, you may go ahead and use your own set of data for these 4 readings. If you don't have it, then you can use the extra spreadsheet that I'll have with sample data on it. Don't use these numbers because I've already used them, or use the other ones that I'm giving you as an option. Okay, so next, our third exercise, we're going to do the same thing, except that we are going to do it for the dry cal device, right? And the dry cal device looks quite a bit different, doesn't it, right? The dry cal device, let me get a picture of it. So the dry cal device actually uses a small piston that's in this window. It's a tube with a piston in it that's visible inside this window. Okay, now what happens is that air from our bubble burette is going to, just like with our rotometer, we're going to check the efficacy of this dry cal calibrator. Air is going to go through our bubble burette, through our trap if we have it. We didn't have one as it happens, into the bottom of this dry cal calibrator and out of the dry cal calibrator to our pump. So air is going to be continuously drawn through this sampling train. Okay, now when we're ready, what we can do is we can start a bubble flowing up through this bubble burette. And we can measure how many seconds it takes for 1 liter of air to pass through the bubble burette. We'll time that. The bubble will take the length of the 1,000 milliliters or 1 liter of air. We record our time, and in the meantime, air is still traveling through here. Okay, by pressing this small button on top of the dry cal, after that bubble has made it's gone through its path, we push this bubble on the top of the dry cal. A solenoid diverts the air from around this dry cal calibrator through this small piston and to the pump. So pushing that button forces that little piston in that tube to do the same thing that our bubble is doing. Now, instead of our eye measuring the amount of time that it takes for the air to move through this column, the dry cal calibrator does it optoelectrically. It's got sensors and LEDs in it, so it actually measures very quickly how long it takes that piston to travel that distance. Push the button, and it reads out liters per minute. Okay, so we have 2 pieces of information we're recording here. Each time with the pump running at a low volume, at a higher volume, at a higher volume, and at the highest volume. Okay, so we're going to get 4 readings, and we're going to determine how fast the dry cal calibrator says that air is moving, and compare it to how fast our primary standard, the bubble burette, says that it's moving. So we're going to go ahead and take a look at the data that we've collected. Here's the data that we've collected for our dry cal calibration. Okay, 1.1 liters took 55 seconds for the burette. When it took 26 seconds, we pressed the button, and the dry cal told us it was 2.3 liters per minute. And when we took the high reading, high pump setting, took 18 seconds. The dry cal calibrator said we were moving air 33.2, and 13 seconds represented a reading of 4.5 on the dry cal calibrator. So let's calculate what this number of seconds really represents. So it's going to be equal to 60 divided by the number of seconds it actually took for the air to move through the through the bubble burette. Okay, and that's 1.09, very close to our 1.1. And I'm going to copy these all down so we can compare them. Okay, well, let's see, 2.307, 2.3, 3.3, 3.2, 4.6, 4.5. Certainly a lot better than the results that we got using our burette. Our dry cal calibrator is almost as good as our primary standard, our burette, right? So it's a very reliable mechanism. Okay, we have to make sure that it's certified for the manufacturer once a year, and it doesn't hurt for us to calibrate it. Test it with a burette to make sure that it's reading correctly in the range that we're going to be using it. Again, dry calibrate a lot more convenient than a bubble burette to carry out into the field to do calibrations, but at the same time much more accurate than say much more accurate than a rotometer, a bit more mechanically sensitive perhaps than a rotometer, which is kind of bulletproof, and quite a bit more expensive than a rotometer is, right? So a dry cal calibrator is a good alternative to a bubble burette. That's way more accurate than a rotometer might be. In fact, very rarely do you see rotometers used in the field for low flows. You do see them frequently when you're measuring high flows, where a slight ambiguity in the reading of the rotometer may not have quite as high a percentage effect on the error, especially if you calibrate it, than it would on a very low range, where it's kind of hard to read small differences in the flow rate on the little ball in the very short scale. Okay, so you could also, if you wanted, this is an option for you. You could also use the volume that we observed in the dry cal calibrator and the volume that it represented in the burette for each one of these different flow rates, and you could also create another uh, uh, another calibration chart for the dry cal calibrator, similar to our rotometer, if you felt that you have the time to do it. So you might want to give that a try. Okay, and finally, our last exercise is actual use of the rotometer in the field in place of our primary standards, like the dry cal or the burette. So how would that work? Well, we're connecting our rotometer to our pump in the field, right? Our rotometer is reading 1.9 liters per minute. It's telling us that there is 1.9 liters per minute of air moving through this pump. Well, fortunately, what have I done? I have created a calibration chart for my rotometer. I'm going to go back up to it here. Okay, so when the rotometer is reading 1.9, the actual flow rate is really looks like 1.7 liters per minute. So I can go back down here and I can say, let's see, the corrected reading is 1.7 liters per minute. Okay, so let's take a look at this. The average flow uncorrected is 1.9. The average flow rate corrected is 1.7. So what is the percentage difference? It's going to be equal to, whoops, it's going to be equal to 1.9 divided by 1.7. So it's about a 12% difference for our reading. In other words, if we had not used our calibration chart, our volume flow rate, our volume measurement, the amount of air that we were testing, would have been off by about 12%. Would have been about 12% higher than we should have read. Okay, so I'm going to give you blank sheets like this for you to fill in. The red portions are the blue portions are the data that is collected in the lab. The red portions are calculations based on that data. And I will give you two versions of this sheet. One version of this sheet is blank and you can fill in your own data. And the other version is sample data that you can use if you are unable to collect your own data, or if your team, if you're out of contact with your team and you can't get access to your data. Okay, so I'll make sure that's posted soon. Okay, hope that helps go through these four various exercises that we have here. First exercise, just simply using the bubble burette to figure out how fast air is moving through the pump. We take 3 readings and average them. Second one is to compare readings that we get on the rotometer and the burette for various speeds that the pump is set at. And we picked out four rates. Okay, the third one is doing the same thing with the dry calibrator to demonstrate how much better the dry calibrator is than the rotometer, how much more accurate the dry calibrator is than the rotometer. And then finally, simulation in the field of what would happen if we only had the rotometer with us and we had to use that chart, a correction chart from a previous calibration of that rotometer with a bubble burette as we had done here. Okay, so that we could trust, get more reliable readings than we would have otherwise. Okay, so I hope that helps. Hope that helps you get through it. So please upload two things. Please upload one calibration lab sheet with these 4 exercises based on your uh, either your measurements, or you can use the sample measurement sheets that I'll give you, other than the numbers that I'm using here. There'll be different numbers, but you'll be able to use them instead. And also then answer the questions at the end of the exercise. They ask you various questions about technique and your expected results. Okay, good. Hope this helps.